Hello everyone, today we have our chapter 8 lesson. Really what we're going to do in this lesson is build off of what we've already seen in linear regression, give a little more insight and a little more details when it does come to finding that line of best fit. So it may seem like this should go without saying, but linear regression is strictly for linear patterns within our scatter plot. So before you go through all the work of finding a line of best fit or a linear model to form around our scatter plot, you want to make sure and ensure that you actually have a linear pattern. Now, of course, we can look in our scatter plot and try to determine, is this linear, is it nonlinear? You can go that route. But really the final judge when it comes to determining if we have a linear pattern that is suited for a linear model is to look at that residual plot. So if you remember the residual plot, we take our line of best fit, tilt it horizontally, and then we look at the residuals or the distance from the line of best fit for each of our points. And the key thing with that residual plot is we hope that we see no pattern whatsoever. So if we see a pattern, as we do here, there's a very clear bend in our residual plot, that would mean that a linear model is not appropriate. So if we saw random scatter, no clear pattern whatsoever, that's a good thing. That means a linear model is appropriate. But in this case, we would say, sorry, there's a pattern in our residual plot, so we should not find a linear model. There are other tools, we're not going to talk about them in class, but where we could find a different model to fit that pattern. If you look at your scatter plot and you're trying to determine, is this linear, is it nonlinear, sometimes that's all we have access to, is that scatter plot, and we just kind of have to make our best bet based on what we see in that scatter plot. However, if it is the case that you are provided with a residual plot, just know that the residual plot is the final judge in whether or not a linear model is appropriate. So in your scatter plot, if you see a linear pattern, you don't have a residual plot, perfect, just go with the linear model. That's the best that you can do. But if you're given the scatter plot as well as the corresponding residual plot, that is where you want to look at the residual plot and say, is there a pattern in the residual plot or is there random scatter? In the residual plot, if you see no pattern whatsoever, that means yes, a linear model is appropriate. But if you see a bend or any weird patterns within the residual plot, that means a line is not appropriate. So when it comes to determining is a linear model appropriate, if you have access to that residual plot, that will be the final judge. The next idea I'd like to talk about when it comes to linear regression is the idea of extrapolation. And really what extrapolation is if we have collected data, in this case for ages 0 through 3, and we were collecting the weight of 0 through 3-year-olds, extrapolation is when we assume that that same linear pattern is going to continue beyond the data that we've already recorded. So in this case, we see that from ages 0 to 3, we have some pretty hefty increases in weight from 0 to 1, 1 to 2, 2 to 3. But if we continue to assume that that same growth pattern is going to continue to, say, age 80, this is where we run into some problems. Because if you think about it, it's not really realistic to assume that somebody's going to continue to gain about 7 pounds every year until they perish. That just isn't how humans grow, how they work. So that's what we call extrapolation. So anytime that you venture into new X territory, this is what we call extrapolation. So what do I mean by that? For example, if we use this same pattern to try to predict what is the weight of a 3-year-old, that's totally fine because we have collected data from 0 to 3 years old. Now, if it comes to predicting the weight of a 4-year-old versus a 60-year-old, 60 is much further away from 3 years old than 4 is, so that's going to be much less reliable than, say, a 4-year-old. So again, anytime that you try to make a prediction beyond the X values that you've already collected, this is called extrapolation, and we want to avoid it as much as possible. I've got an example here to maybe illustrate why extrapolation is not a good idea. So let's just say we have data on the first 4 5K races for a team, maybe a cross-country team, and we see that on race 1, we had a typical 5K time of 19.75 minutes. Race 2, we get a little faster. Race 3, we get a little faster. 4th, we get even faster. So as we can see, we're getting much faster over the course of each race, and that kind of makes sense, right? We hope that happens in a cross-country season. So based on these 4 data values, so 1, 9.75, 2, 18.94, and so on, I've come up with this race time prediction based on what race number it is. So if this is the first race of the season, I can predict your race time by putting 1 in for race number. If it's the third race of the season, I'd put 3 in here, and so on. And again, we're trying to predict race time based off of that, or 5K time. And actually, if we look at a scatter plot of this data right here, the correlation is really, really strong. It is a strong and negative correlation, almost equal to -1. So if we assume that this same growth or this same pattern is going to continue beyond the 4th race, let's say, for example, we want to predict what the 5K time would be for a runner in their 12th race of the season. Well, let's see what happens if we do that. So again, I have my predictive equation for the 5K race time based on what race of the season it is. Again, we want to know what is the predicted time for the 12th race of the season. Maybe it's a state meet for a 5K. Well, what I'm going to do is just plug in 12 for this race number because it's the 12th race of the season. And if I take -1.031 times 12, I'll get -12.372. And then if I add that 20.830 to it, this gives us a predicted 5K time of under 8.5 minutes. If you're not familiar with a 5K, that is just over 3 miles. So I apologize, but that is simply not going to happen. So again, this is just one illustration of why extrapolation really is not a good idea. We cannot continue to assume that a pattern will continue going on beyond the data that we have already recorded. One last thing here on extrapolation, just a comic that I found. So yesterday he had 0 wives, today he got married, so he has 1 wife. So if we were to extrapolate, tomorrow he'd have 2, next day he'd have 3. Very satirical, but another illustration of why extrapolation is maybe not a good idea. Last thing here that I want to talk about are outlier points, leverage points, and influential points within a scatter plot. So the first thing is that in a scatter plot, if we have any point whatsoever that stands away from our general trend, that is what we call an outlier. So outlier is a very inclusive term. Obviously, in this scatter plot that I have, these blue points are not outliers. This red one up above is an outlier. So just know that the outlier is any point that stands away from your general trend in the scatter plot. And a single outlier can have a significant impact on the overall linear regression line. So that is why we want to pay special attention to them. Just an example of how much an outlier can impact the line of best fit. The blue line here is what our linear model would look like without the red point. And this red line here shows what it would be just with adding that one outlier point. So we can see there's a pretty significant difference in our slope. Even though we have quite a bit of data in this scatter plot, that one point has a lot of influence on it. So just be aware of when you have outliers and how that could impact your line of best fit. Another type of special point that we can have in a scatter plot is called a leverage point. So a leverage point is a point whose x-coordinate is very, very far away from the rest of your data's x-coordinates. So for example, if we look at this scatter plot, most of our points are between an x-coordinate of say 0 and about 1.5. So most of them are far on the left here in our scatter plot. Now, if we look at this point all the way out here, I think we all agree that this is also an outlier, but because its x-coordinate is almost at 5, whereas the rest of them are all below 1.5, this would also be what we call a leverage point. And the reason we call it a high leverage point or a leverage point is because it has the potential to significantly impact what our line of best fit is. So for example, if it is very much in line with the rest of our data, it can actually strengthen our correlation. But if it is further below, it can really alter or weaken our correlation. So again, any x value that is really, really far from the rest of our x values, that is what we call a high leverage point. The last type of special point that we have is called an influential point. And this is one where if we omit it or take it out of our scatter plot, it will significantly influence our line of best fit. So for example, if we were to include this red point in this scatter plot, that's going to definitely pull our slope down, kind of in that downward direction. But if we remove that red point, it's going to pass right through our blue points here. So in this case, the red one would be an influential point, as well as being an outlier. It would have an extreme influence on our line of best fit. So the last thing I'd like you to do is if we look at these 3 points, A, B, and C, I want you to pause the video for a moment and just determine of these points, A, B, and C, which one of them would be considered outliers, which ones would be considered leverage points, and which ones would be considered influential points. So take a moment, pause the video, and see if you can determine which would be each of those. You will have multiple outliers, multiple leverage points, and multiple influential points. Okay, so hopefully you took some time to identify or think about which of these points would be outliers, leverage points, and influential points. I'll remind you, for outliers, these are any points that clearly stand away from our general trend in our data. So obviously most of our data is right here in this mass of red points, and I think we would all agree that all of A, B, and C very clearly stand away from the rest of our data. So in this case, all of our 3 points, A, B, and C, are considered outliers. Now, when it comes to leverage points, again, these are any points with x coordinates that are far away from the majority of points. So in this case, if we look at point A, that is right in the span of x values that we have for the rest of our points. So that actually would not be a leverage point. But if we look at B, that's very far to the right compared to the rest of our data. And so is letter C, that's much further to the right compared to the rest of our data. So in this case, our leverage points would be B and C. And finally, influential points. Again, these are points that if we take them out of our line of best fit, they will have a significant impact on our line. So for example, if we look at letter A here, without letter A, our line is going to pass right through our points. But by including A, that's going to tilt our line up, steepen our slope a little bit. So A would be an influential point. And same thing with letter C. If we include letter C, that's going to drop our slope quite a bit. But if we look at letter B, B is right in line with the rest of our data. So even though it is an outlier and even though it's a leverage point, it actually would not be an influential point because it's not going to significantly alter our line of best fit. So hopefully by now you're feeling pretty confident in identifying outliers, leverage points, and influential points. And I hope you also see the impact that extrapolation can have on our linear analysis.